This is 6 rectangles. So, what is a rectangle? A rectangle is a parallelogram with 4 right angles. Sounds similar to a square. But a rectangle has different properties compared to a square. For example, opposite sides have to be parallel and congruent. Same thing goes with angles. So what parallel and congruent means is pretty much whatever this angle is here is equal to any other angle pretty much on the rectangle. Consecutive angles are supplementary, so these are consecutive, just those. They equal 180, which is supplementary. In total, they add up to make 360. The theorem that we would most be using for our practice problems will be how diagonals that bisect are congruent to one another. So what a bisect is pretty much the crossing of two lines in between a rectangle. So this would be our bisect. And whatever would be on this line, for example, x, and y would be equal to one another. Y could also be here. X could possibly be there as well. It doesn't matter where they are, as long as they're on opposite lines, they're equal to one another. So let's go ahead and do an example problem. Okay. To draw the rectangle. My drawings aren't that great, by the way, but I try. Okay. So if FD equals 3x minus 7 and EG, oh, I'm sorry, I didn't label. DGF. Okay, that's your labels. Okay. And it's also bisecting. Okay. EG equals x plus 5. So since we know FD and EG are equal to one another because the property that we just used, diagonals bisect each other. So the diagonals that bisect each other are congruent, which is equal to one another. So pretty much what this means, and we're trying to find find EG. Okay. So we use this FD. Since we know it's equal to EG, we can just put equal signs, and it's just a regular equation. So 7, 12, 2, and x is 6. But that's not your final answer. The question says to find EG. So we replace the 6 with this x right here to find EG. And that's simple. That's 5 plus 6. That's 11. And that's pretty much your answer to the problem. Okay. The next example problem is we're using like the same rectangle, same concept. But the question is changing a little bit. Equals 2x minus 3. Boop. DFG is equal to x plus 12. So since that, this way would be our angle. We're leaving this part open, which is 90 degrees, and DFG. So we're going the same route, and we're leaving this part. So, sorry, let me draw the arrow there. Okay. So it's pretty much like almost going in a circle around the rectangle, if that makes sense. So, since they're not necessarily equal to one another, we would do 2x minus 3 plus x plus 12 equals 90 degrees. Because we're just trying to find, send these two parts, they equal 180. So we're trying to find both by making it 90. Okay, so we got 9 plus 3x equals 90. We subtract, we get 81. I'm going to move this over here. 81. Divide. X equals 27. I think that's right. Okay. So like I said before, we are trying to find EFD. So we have to substitute 27 back into EFD. Let's just write it up here. Okay, so 2 times 27 minus 3. That is 54 minus 3 equals 51. Therefore, making angle EFD 51. Okay, so the next few set of problems we will be doing is A4 trig. Trigonometry is the measurement of triangles, and we measure triangles by using trigonomic ratios. So you may have heard of these trigonomic ratios before. They are sine, cosine, and tangent. So we use these three as pretty much formulas to understand the measurement of a right triangle or a triangle. So they have formulas. For example, sine has opposite over hypotenuse, Then cosine has adjacent over hypotenuse. Then tangent has opposite over adjacent. So this is what we would use for like an example problem. Like I'll just give you an example here, honestly. Hold on, let me draw it real fast. Okay, that is a right angle. So since 61 is in the box, we will use it. Okay, so we know x is the hypotenuse, because if we flip it to the side, we know that this is the right angle. This is the opposite of 61. We're going to go off 61 here. And how do we know what goes off 61? Well, we usually go off whatever's inside the triangle. So in this case, we always trying to find x. So we know x is the hypotenuse and 24 is the opposite. So out of these three, sine is the only one that has both the opposite and the hypotenuse, which is the only reason why we would use it in this case. So we would set up a problem, sin, aka sine 61. So what this means is there is a chart that usually would give you the decimal of sin 61. In this case, I don't have it with me, but I do have a calculator, so that will work. Okay, so sin 61, that's 0.8796, around that, and equals 24. Oh yeah, okay. So pretty much this is equal to the opposite over hypotenuse. So it's 24 the opposite, x is the hypotenuse, 24 over x. So now you want to cross multiply, then it'd be 0.8796, x equals 24. So once you have that, then you divide because you want to get x by itself. Ooh, that is weird for. Okay. So in this case, you would get 27.44. That is your measurement of x. That is what you would get by using a sine. So this is pretty much a flat example, great example problem to use for basic beginners of trigonometry. Yeah, that's pretty much it. So this is 10-4, inscribing angles. So what this is pretty much, it's an inscribed angle. It has a vertex in a circle, and has sides that contain chords. So these are the chords and the vertex. So there's three types of ways we can a circle can be inscribed. So there's this way. There is also there's this way. The inscribed angle would be right there. And then the third way would be if it was outside the vertex. This is on the line, by the way, I'm sorry. If it was outside the vertex. So by using these three ways of inscribing angles, we can understand how the measurement of a circle and how it's inscribed, or if it's inscribed or not. So the theorem we'll be using is if an angle isn't, inscribed. Let's use A, for example. So this is an inscribed angle. If an angle is inscribed, then the measurement of the angle equals 1/2 of the measurement of its intercepted arc. An intercepted arc is pretty much BCD. It's pretty much like this angle surrounding your inscribed angle. So for example, say if, hold on, let me move this. So if A was right here, whatever this would be, it would be 2 times whatever A would be in this case. And if the A was out here, it would be 1/2 of what A was. So what we'll do here is pretty much do an example problem. It's pretty easy. So for number 1, we'll find measurement B, and we'll do this. And since 30 is our inscribed angle, or measurement, okay. So since 30 is inside the circle, we want to move out. We want to figure out what this number is here. And since the formula said 1/2, in this case we wouldn't do 1/2, because when you're moving to the outside of the circle, which is a bigger angle, a huge, like 2 times the angle, in fact, because you would do 30 times 2 to equal 60. Then x would equal 60. The farther you go out in a circle, the bigger the measurement will be. So that's pretty much how you do it. So if 60 was out here, hold on, let me redraw this. Okay. So another example. If 60 was out here, then we would do, times 1/2. Because then you're going smaller. You're going into a smaller angle. So this is how you really figure out and understand why sometimes it's times 2 when sometimes it's times 1/2. So it's pretty much that's pretty much all of it really. This is pretty basic. It's like beginner, and it eventually gets a little bit harder, but that is not what we're getting into today. So another version of this will be, hold on. Okay. So another example is MRT, measurement RT. Circle. Boom, boom. It's the same thing, same exact thing. And we have 63 in here. So that must mean 63 times 2 would equal 126, making this 126. And it's the same thing. Well, hold on, let me maybe make this a little bit better in this case. Okay. Okay. So, like we just said, if we didn't have 63, cover the 63, we would take 1/2 of 126, and that would be the smaller angle. But in this case, we'd have to do 63 times 2, which is 126. And since we got 126, which is doubled pretty much. So that's pretty much mostly inscribed angles. It's just pretty simple right now. The theory that we used a lot was the inscribed angle theorem, which is 10-6. And I'll repeat it again because this is really important all throughout inscribing angles. If an angle is inscribed, then the measurement of the angle equals 1/2 of the measure of the intercepted arc. And like I said, to review, this is the intercepted arc. And like I said, if you don't have this, it's 2 times 2. If you don't have this, I was wrong. If you don't have this, it'd be times 1/2. If you don't have this, it'd be times 2. So that's pretty much the overall theme of inscribing angles.